Hello guys, this is EDU-WIZARD with a new video, and in this video we are going to discuss about the topologic optimization of a bracket. Before moving into the video, make sure that you subscribe the channel and like the videos and share the videos. Okay, let us begin. First, go towards the analysis settings. In the analysis settings, select the static structural. The design modeler is loading, and now we have the window open over here. Let us select the XY plane and look at option is given, and we will be drawing that. Go to the sketching, then select the rectangle portion. Okay, the rectangle is selected. And the rectangle is being drawn, and now we need to give the dimensions towards the rectangle. Both the width and the length need to be assigned. Okay, then we can specify the dimensions. Dimensions are given in the units of millimeters, not meters. Horizontal dimension is given as 45 and the vertical dimension is given as 65. Then we need to draw a diagonal. Okay, the rest parts need to be trimmed away. Only half of this rectangle is required. Okay, I have trimmed all the parts, and now I need to draw 3 circles. 2 circles for supports and 1 circle is for applying the load. The circles are having the diameters 5 mm. As we are just learning, I am not taking the exact horizontal and vertical directions for the circles. The exact positions of the circles are not taken, as we are just learning the topology optimization. We do not require an exact result. Okay, dimensions are provided for the circle by using the general dimension tool, and every circle is given the dimension of 5 mm. Okay, now let us fillet the 3 edges. The fillet radius is about 5 mm. I am altering the fillet radius to 5 mm. Okay, one edge is completed. Now the next edge is also completed, and the third edge is also filleted towards 5 mm radius. Now let us extrude that. Go to extrude, double click on it. Then the geometry is specified. and I am giving the depth of about 10 mm. Now generate the extrusion and we get the following figure. Okay, that is completed, and let us click on the generate option and move towards the modeling section. Double click on the modeling section and modeling section will be loaded. Okay, we have opened the modeling section. Here we need to specify the fixed supports. I earlier mentioned that the two circles, two holes are fixed supports. These are provided as the cylindrical supports and one of them is provided as the bearing log. Let us check the geometry which is assigned as matrix structural steel or no. That is a material that I am going to use, structural steel. Now let us mesh this. Go to solve. Meshing is being proceeded over here. Then let us insert the cylindrical supports. Okay, you can see that I have right clicked the static structural, but it is not visible due to the screen recording trouble. Okay, I am applying the two faces, two holes as a cylindrical support. Then one of the faces needs to be assigned to bearing load. The bearing load is given in X direction and Y direction. In Z direction it is impossible to give since it is parallel towards the axis. Okay, now we are assigning the load. And in the X direction I am giving a load of about 20 Newton. And in the Y direction I am giving a load of 50 Newton. Therefore, there are two bearing loads. These are given separately. And now I have applied the equivalent stress and deformation values in the solution and I have solved. The following is the result of the solution. You could see that the sky blue color is located on the left side and on the top side, while the right side is excluded away from it. Right side is only having the blue color. That means that there is less stress concentration in those regions. And in the topmost, on the right side, on the topmost corner, there is a red color. This means that maximum stresses will be concentrated there. So more material needs to be concentrated there to withstand all these stresses. I have altered the X direction stress towards the 50 Newton and let us see what is the change. The equivalent stresses have increased gradually in those right side bearing load portions. Now let us move over towards the Topology Optimization section. In the analysis settings, draw the topological optimization towards the static structural that we have performed earlier. And now you can open the setup section in the Topology Optimization. And the setup section is now loading. Okay, this is the window of the setup section and you could see the following steps that we have done earlier are listed above the topology optimization. the static structure, the bearing logs, the cylindrical supports are all listed. And I have solved the topology optimization. The only thing that we need to alter is the response constraint. Response constraint, I am fixing it over towards 50%. Optimization region is a region which we are optimized. The objective need not be altered, and the red color portions are the exclusion portions. And only thing that we need to alter is the response constraint. By response constraint, the different types of the response are there, including the mass, volume, etc. And I am only performing it on mass, and the percentage of the mass that is required to be optimized is 60%. That is being offered. And let us again solve it. Now we can obtain the result of the solution. The solution is in two types, that is topological density and topological elemental density. In these two types you have the solution. Let us play the animation video. You can see the material removal over those areas where stress is not concentrated. On the left side portion, there is less stress concentration, so more material is being removed from that. While the right side, where there is high stress concentration, the materials are very rarely removed. Now let us export this file, STL file. Okay, now we can open the static structures again to modify this obtained result. This is not good for manufacturing. So we can open the STL file that we have already saved, and then this STL file is being imported as a geometry. And now we can see that in the design modeler, this geometry is visible, but this geometry is not properly utilizable for manufacturing purpose. Therefore, we need to modify this geometry, and we are making this geometry much more standardized shape. We can draw an oval shape. The oval is selected from the sketching, and now oval is being drawn. And again, one more oval can be drawn. Now we can trim away the parts. Before trimming, we can include the hole portions. These holes are made into the circles. Two circles can be placed. As I told earlier, this is for just learning, so the circles are not exact locations. Now go to the modify, take the option of trimming. Now trim away the unwanted parts. Okay, fine. After finishing this trimming, now we can extrude the part and remove or hide or suppress the original geometry we obtained as a result of the topological optimization. Okay, I am giving a depth of about 10 mm for the extrusion. Now I am hiding it. I have generated the extrusion and I have hidden the earlier geometry. Now this is our topological optimized bracket. Okay, fine. I hope you could understand the topological optimization in simple words and simple languages. And now, please subscribe the channel for more videos and for more analysis and simulation.